The modern visualization framework provides a wide range of mapping procedures based on geometry and material modeling. However, all richness of mapping is reserved for surface objects. The visualization of volume objects is limited to volume rendering technique, customized only by a transfer function. In this work, I will consider a problem of visual analysis of dynamic multiscale heterogeneous objects. Such objects that have complex material distribution demand flexibility in geometry and materials modeling, and that should be a part of visual pipeline. Here is a brief example of the type of visual analysis problem that I consider. So, how it is done? I consider an accelerated GPU raycasting as an inspiration and the core of a parallel visual pipeline design. Heterogeneous objects have a non-homogeneous material distribution that is modeled on a set of geometry subdomains. The volume raycasting of such objects can be described with the following steps presented on a slide. The technique is usually applied for objects modeled with a basic convex primitives, such as tetrahedron or sphere. In this work, I will consider a geometry representation as a signed distance field. An SDF framework provides a unified solution for arbitrary complex geometry and material with dynamic features of various scale, and, as well, a unified ray primitive intersection procedure. Arbitrary geometry and material are modeled mostly through functional superpositions. The modeling logic is often presented as a graph that is referenced as a constructive tree. In this work, the constructive trees are a reflection of visual pipeline logic. In most cases, we can optimize the constructive tree evaluation by splitting tree into local subtrees with bounding subvolumes and loading a right subtree on demand. This is important as dynamic and multiscale features are considered. In the presented previously video example, we used the introduced parameter values to load on demand the multiscale constructive tree representation and defined bounded volumes for its further splitting. Technically, in terms of visual pipeline design, the programmer has flexibility in handling both modeling and efficiency optimization aspects. The introduced subdivision has to consider both geometry and material modeling aspects. In digital fabrication, the volume material is modeled as a set of homogeneous regions and blendings between them. Very often, there is a correlation in the material geometry regions and geometry used in SDF constructive tree. This simplifies the further subdivision task. Here is an example of some arbitrary dynamic variations in shape and topology. I was much inspired by object-oriented principles in data flow design that allow building a visual pipeline as a Lego in VTK framework. So, in this work, I have explored the possibilities of that introduced by Optix default and callable programs to imitate the object-oriented tricks for GPU pipeline construction. It turned out that callable programs are great for GPU implementation of constructive modeling with time distance functions. However, callable structure can significantly slow down the rendering of large heterogeneous objects. The conventional visualization tools specify the input data possible geometry and topology descriptions with various dimensions considered. I take advantage of this assumption in the design of the optimal class hierarchy and suggest mainly one callable program for developer to specify, the SDF primitive. As well, such cases as tetrahedral meshes demand volume sampling applied after primitive sorting. So, the material and SDF geometry callable program IDs should be sent to renderer class. For most of presented examples of heterogeneous object visualization, the pipeline implementation has the following VDK similar structure. So the features and acceleration structures of GPU raycasting can be used as a core of heterogeneous object visual pipeline design. Moreover, such view can provide a lot of flexibility in both modeling and performance optimization control.